They're not in general vector spaces, so they're in general they could be very weird.
Okay, so the second one is nonlinear. So okay, so arc spaces, not Jet spaces.
Yeah, so arc spaces for me are infinite dimensional. And,
Okay.
They're adjoints to comonads.
Okay.
Easy. So it actually shows your screen.
Okay.
So you can switch between them.
I can switch between them? Or
I can switch.
Okay.
Do you want to be visible at the moment, or you want?
Yeah, we can put this on here for this is fine.
Mm-hmm.
Okay, so
stand in front of it.
Yeah.
Doesn't matter if he stands in front of it. It just shows the screen.
Yeah.
It's not.
Just broadcasting the slides.
Yes, it's just.
All right. So should I start or?
Yes. So please start.
Okay, and then I just press spacebar over here, I guess.
Or arrows.
Okay. So thanks for having me here. So I'm going to be talking about some things that I've wanted to think about while I was at MSRI, but I kind of forced myself to talk about this subject. So I'm not really an expert in this, so be wary. Okay, so there's this text that's not supposed to be there. Okay, anyway, so there's a classical theorem of Mordell. So you have a curve that's defined over Q. Right, and so this is proved in 1984. So if you have a curve that's defined over Q and its genus is bigger than or equal to 2, then there are only finitely many rational points. Okay, so this is Monon theorem. What it remains to be known is we don't know how big this number is. So knowing how big how many rational points there are in some way is known as effective Mordell. Okay, and this is the effective problem. So my animation now would have slid that up to the top, but it's not there. Okay, so there's kind of two answers to. I mean, I should have put a bunch of other people here other than Boone, but there's kind of two answers that you can have, right? So one answer to how many rational points there are could be in terms of height estimates. The other type of answer that you could get would be from an actual bound. Okay, and so. So this is a theorem of Booleans where you're in the function field case. So if you have a curve of genus bigger than or equal to 2 in the bottom case, and you're working over a field with a derivation, a non-trivial derivation, and C over K is not isotrivial, I'll talk about what that means in a little bit, then you have this explicit bound on the number of rational points. Here, so n, when I do a factorial and it's raised to some number, that means that you that means that you apply factorial that many times. Okay, and so this n here will be some invariant depending on this. So it could be like the rank, and it could depend on the genus, and certain intersection numbers. All right, and so I am going to focus on this type of answer. And yeah.
Do you mean just C of T, not the algebraic closure?
So yeah, I guess. C of T, no, I think, so...
There are infinite number of rational points over the algebraic
So
closure.
C of T, it should be C of T yes, sorry, yes, that's exactly, yeah. Sorry, this is supposed to be intersected with gamma, and gamma is supposed to be the, oh man, that's really bad. Okay, this is supposed to be C of T, yes.
Okay.
Thank you very much. Yeah.
And the same thing in the other one.
Yes. Okay. So wow, I hope I don't have this everywhere. Okay. So so this is so man, this is really bad. Okay, so this is supposed to be intersected with. Okay, so there needs to be a big correction here. I don't know why.
I just don't know why.
Okay, so
wait.
Can you go back to the previous slide?
Yeah. Yeah, those should not be algebraic closures.
So in the first one,
yeah,
it also should be Q, not.
Yeah, it should be Q.
You're sure?
Yes.
Okay.
Yes. Yeah, okay. Yeah. So there are infinitely many. So actually, for points of bounded height. So now I'm confused. I don't know about the first one. The bottom one is definitely wrong.
Okay.
And it should be C of T.
Okay.
Yeah. And then over here, this should not be FP bar. So this should be FP of T. So. I had before on the slides, I was having this intersected with a group, and then I deleted it, right?
Okay.
So that's, I shouldn't have done that. Okay, so so what I want to talk about today is the bounds of these types. Okay, so these are examples of theorems. I'm going to have to explain what these things mean. Okay, so this is one type of problem, and so another type of problem that you could have would be so the number of rational points. Again, this shouldn't be C of t. This shouldn't be algebraic closures. Okay, but so like here. They should be intersected with the C of t points of the variety. Okay, so so there's two kinds of problems that I want to consider today. One are the type of effective Mordell statements, and one are the effective Manon-Mumford statements. So these are the number of points on a curve which are torsion. So you embed a curve into its Jacobian. Jacobian's an abelian variety. And you can ask, then it has torsion points, and you can intersect the curve. Sorry, with the set of, I need to be quiet. Okay, you can intersect the curve with a set of torsion points, right? And this is finite. Okay, and then and you'll see in red there are certain numbers that are appearing all over again, and these will come from intersections in jet spaces. For example, this will be the degree of some cycle. This is the degree of some cycle. So these proof techniques are the same. And then here, the blue ones are using the same kind of proof techniques that Alex did in so these geometric jet spaces. All right. So again, those should be rational points at the top. Okay. So again, this is an open problem. So getting a bound for the rational points. Okay, for a curve. So in each of these cases, I was trying to organize it by function field, right? And then characteristic P function field, and then number field case. Okay, so as I said, this normally would have been an animation. In here, again, this is the algebraic closure is going to be the death of me today. Here I'm going to look at these two specific instances, so I can demonstrate the proof techniques here. Okay, and so to get an idea of what this one says here, so for this one, if you have a finite rank subgroup of the abelian variety, so you take the algebraic closure points of the abelian variety, and then you can consider a finite rank subgroup in there. This bound here, for example, will be asymptotic to this for large rank. So this is something that you could have. Yes.
Naive question. In the top line, you have a curve that you are counting points on, and suddenly there is an abelian variety and the rank and a finite rank subgroup. Who is the abelian variety? How is it related to the curve?
Oh, okay. So the abelian variety is the Jacobian of the curve, and in the top one, the finite rank subgroup is the rational points of the abelian variety. Okay, or you can take it to be other things. Okay, so. I'm going to start with the top one. First, I need to talk about descent, and I tried to formulate descent in such a way that it would work for all the three different cases. Okay, so and it turns out, so later on, I think the characteristic P case gets a little messed up. But okay, we're going to call K0 a subfield of K descent field if there exists a derivation which is non-trivial on K, and K0 is the constants of the derivation. So like, if you do pth powers in characteristic P, this would work. Okay, so so we're going to say that x over K descends if there's a subfield, a descent field, such that x is tensored up. It comes from something defined over K, and you tensor up via K to get it. Okay, we're also going to call it isotrivial, right? If you have an isomorphism after taking algebraic closures. Okay, so you have the same thing, but now you're just going to take algebraic closures. Okay, and so if you have an abelian variety, for me A is always going to be abelian variety. A trace 0 means that it's going to have no subvarieties that are isotrivial. Okay, so it's going to have no sub-abelian varieties, not just subvarieties, sub-abelian varieties which are isotrivial. All right. Okay. So this says that there's an abelian variety which is isotrivial. So B, I use A's and B's for abelian subvarieties. Then B is going to be equal to 0. Okay, so that definition was supposed to shrink up to there. Okay, and I was going to give you an example of things which are isotrivial and non-isotrivial. Okay, so here is a family, right? If you consider this as something defined over C of t with coefficients in C of t, you can see that this is kind of trivial, right? So it actually just looks like a product, right? So it's really defined over the integers even. Here, this one actually turns out to be a non-isotrivial family, and to prove that, you have to show that there's non-isomorphic things in here. So, yeah, so this is an example.
Quick question.
Mm-hmm.
Do you know if there's a purely algebraic field theoretic condition on K0 for K0 to be a descent field? Imagine that somebody doesn't know anything about derivations and just tries to do field things.
Purely...
Like, if I give you a subfield, how
so
would you go about telling?
So there's a minimal field of definition in the geometric case.
No, I'm not talking about isotriviality, just this notion of K0 is a descent field for K.
What do you mean by purely field theoretic?
I give you two fields.
Yeah. Oh, within the theory of field.
Yeah.
Okay.
I give you two fields, how do you tell whether one is a descent field for the other?
So, let's see. So transcendence degree doesn't, because characteristic people mess that up. I don't know. So inseparability messes you up. So I don't know the answer to that.
In characteristic 0?
In characteristic 0, transcendence degree will. So if you have something, so like if you increase your transcendence degree, then and you like so say you take a partial derivative, right, with respect to a certain variable, it'll kill all the indeterminates.
Wait, the partial derivative of what?
So like
I just have two fields.
You have two. Yeah, if you have two fields. Okay, you can't do derivatives. Yeah, I don't know. That's a good.
Okay.
Yeah.
Oh, well, one of them's got to be contained in the other one for it to even make sense to ask the question.
Yeah.
Yeah. Okay.
You know, so then it's just a question of transcendence degree 1 over the other one. Because it's a question about the differentials. You want to rank 1 differentials of K over your subfield.
Wait, what? So you're saying that big K has to have transcendence degree 1 over K0?
Yeah.
One.
Yeah.
Wait, what?
One.
I can
Because
take a
you're
huge
saying
differential.
that there's a differential of vanishes.
But can't I take a huge differential field and look at its the constants of it? The huge differential field is going to have huge transcendence degree over its constants.
I don't think so. Because
Yes.
you're just looking at you need to construct a derivation.
I think we should. Let's talk about this. Let's talk about this after.
Okay.
All right. So. Okay.
I mean,
Sure.
Yeah. Okay, so I'm going to do something that Barry Mazur does to talk about this problem, and so and I'm going to introduce a topology called the configuration topology. Okay, so if you take an abelian variety, right, this actually works in general for groups. What you can define to be, so you can define a configuration to be a finite union of translates of abelian subvarieties. Okay. And you take these to be a basis of closed sets for a topology. So the intersection of configurations is configuration. You can actually do this with cosets of groups too. Okay? And so if I have a subset S of an abelian variety, right, then you can define its configuration closure, right? So this is a subset of points, I guess, to be the intersection of all the configurations that contain it. So it's the smallest one that contains it. Okay, so this is the topology here. Here, I've kind of drawn one, so you can kind of think of these as a union of hyperplanes and points. Okay, so this is if it were like, a vector space, right? So that's the picture there. And that's what you should think about. Okay, oh, that box should not be there. So the Mordell, here's the Mordell-Lang problem, okay? So you have a field, and you have an abelian variety defined over your field, which is trace 0, meaning that it has things that don't descend. And you take S, a subset of your abelian variety, okay? And if you have the appropriate notion of finite rank, right? So you have S, the group that the points generates, S, is finite rank, then the Zariski closure will be equal to the configuration closure. Okay, so the Zariski closure of these points will actually, so it says that once you satisfy this finiteness condition, then your space here is going to be, the Zariski closure has a certain shape. And it looks like this shape. All right, it looks like one of those translates. Okay, and so, so what was supposed to happen was this was supposed to go up, and I'm going to show you an example of a subgroup that has finite rank. Okay, so there's the Mordell-Weil theorem. There's two versions of this, and actually I should say this is characteristic 0 now. So it says that the rational points of your abelian variety are finitely generated And in the function field case, this should say, so trace 0, I guess that's true, so it's not isotrivial. Then this is also finitely generated. So you don't have to worry about constants in this case. Okay? So this is a theorem, okay? And so
What are the conditions on K?
what are the conditions on K? So K is characteristic 0.
I mean, first, it's not true if it's algebraically closed.
Yeah.
Yeah.
Right.
Yeah.
It's true if it's a number field.
Yeah. So
Well, the whole notion of trace 0
so
doesn't make sense
take
over.
K to be Q or C of T with A to be an abelian variety that's non-isotrivial.
So you want
Yeah.
a number field situation.
Yeah.
Yeah.
Or yeah, but there's also a version for function fields.
field.
Well, it's the same thing.
And in the trace 0. Okay. So that's that. So this is an example of a finitely generated group. Okay. And so recall that you can define the rank, right, to be the Q dimension of take K to be Q, right? So the rank is just what you get after tensoring up with Z. So and remember that if you have a finitely generated group, so that your group looks like a free part and a torsion part, right? So this R here will be the rank of this gamma when it's finitely generated. Okay, so now I'm going to explain how this Mordell-Lang problem implies the Mordell conjecture, or the Mordell problem. So I had this statement about configurations being, so when you have this subset, which is contained in a finitely generated group, right, or a finite rank group even, right, then I said that this Zariski closure of that set is going to look like a set of configurations. Okay, so here are the choices that I make. I'm going to take K to be Q. I'm going to take A to be the Jacobian of a curve, okay? And I'm going to take the genus of the curve to be bigger than or equal to 2. All right? So then S, I'm going to take to be the set of CQ points. And it's contained in this finitely generated group by Mordell-Fay. Okay? And so this, by the theorem, or by the Mordell-Lang problem, if we assume it, it says that the Zariski closure here has this shape. It looks like a configuration. Okay? But this configuration is contained in here, right? It's contained in C of Q bar, right? But this thing has its genus bigger than or equal to 2, right? It's a curve, right? So it's not going to have elliptic curves inside of it, right? It's not going to have a dimension 1 abelian subvarieties. So that says that all of these have to be 0, and which says that this is just a finite union of points. Okay?
Why is BI if Q bar contained in C?
So this was the definition.
But BI
So
is a
these two
abelian
things-
subvariety.
So this
You're
is,
translating a abelian subvariety.
yeah, this is a
You don't
trans.
really mean to say it's all contained in C
No,
of Q
but the-
bar.
It definitely
left
is,
one
because here you take the Zariski closure of this, and they're equal, right?
Okay.
Right? They're equal. So
Yeah.
this is certainly, yeah.
Okay.
Yeah. So, so that's that. And so, so this is just a finite union of points from this perspective. Okay.
I'm just not convinced that it's contained in C of Q bar.
Well, C
Do you believe that this is true? That C of Q, Zariski closure is contained in there? Do you believe that C is a Zariski closed set?
Well, the Zariski closure C of Q is C of Q. It's a finite set of points.
It's a finite set. Well, we don't know it's a finite set of
Yes,
points.
we do.
I'm proving
Yes,
it's
we
a
do.
finite. I'm
No,
proving.
we know that.
I know, but
Because we have faultings.
yeah, I know. But I'm showing you how faultings implies this.
how faultings follows from the Mordell-Lang.
Yeah.
Well, if you know it's a finite set, then it's certainly contained in C of Q bar.
Well, so what you have to do is persuade me of the previous slide.
Yeah,
that
I
the
do have to.
Zariski closure was
That's exactly what I'm trying to. That's my job. I need to persuade you of. Yes, I need to persuade you of this statement here.
Yeah.
Okay.
Yeah. Because that's just not obvious from the.
Yeah, it's not obvious at all. That's an incredibly hard theorem. Yeah. Right. Yeah, that's what I'm going to try and I'm going to show you that. Yeah. Okay, so that's my goal. Okay, so this is one example of how this configuration closure, right, will show you that that you can get a finite number of points, okay? So that you know, the number of rational points on a curve is finite. Okay, so let me give you another example, okay? So, so you can take the torsion points in an abelian variety, okay? And so this is another finite rank group, okay? So why is it finite rank? Well, if you take any torsion point and you tensor it up with Q, there's going to be something that kills it, right? So there's some multiple of n that kills it, right? And so you can do n divided by n, right? That's 1. So you have that tensor product. Bring the n over to the other side, and the other side is 0. So all torsion points are killed, right? Okay, and so this is an example of a finite rank subgroup of the abelian variety. Okay? So, so that's interesting. Another thing to notice is, so if we do, these torsion points are actually dense too, right? So I've shown the 2 torsion when you take a C model lattice, so an elliptic curve or C model lattice, and this is the analytic presentation of this. And so if you were to increase the n torsion, right, this would start to fill out and it becomes dense. So what's interesting, right, about the this theorem though is that here you in this case, right, where I take k to be q bar, right, a to be Jacobian, right, of a curve over q bar, and I take the genus to be bigger than or equal to 2, and I take S to be the intersection of these two things, okay? Then this is going to be the same thing as a configuration closure. So for the same reason that we had before, right, that you can't have abelian subvarieties of curves, right, that aren't points for when the genus is bigger than 2, this is going to be finite. This is really interesting though, because this is dense, right? This is a curve, and this dense set only intersects the curve finitely many times, okay? So that's an interesting example of this.
Yeah.
All right, sorry, I keep getting loud, so you just gave up. Sorry. Okay, so I wanted to say the bounds that we know for Men and Mumford. So they all kind of have the same shape, and they're going to have the same trick. So this is, again, the number field case, right? So this is not supposed to be here. So the middle one, and then they have the function field case, and I guess I did the function field case twice. Is that what I did? This is a different one. So this is the messed up one at the bottom again. So sorry about this. Okay, so here are these again. So again, this was supposed to animate and come to these things again. Okay, so, all right, so again, god dang it. Okay, so this thing is supposed to be the C of t points again, so not the CT bar points. So I'm going to try and attempt to show this bound here, okay? And so in this geometric Mordell-Lang, here I'm going to do a similar thing where I take S as a differential algebraically closed field. I'm going to take S to be a subset of AK, and I'm going to assume that A, let's say it has trace 0, right? So it's not isotrivial, right? Let's just say it is trace 0 for the constants of the derivation. So. And then I'm going to do the exact same statement here. But now I'm going to look at in a function field case, and this is what we call the geometric version. And so this is what I want to prove. Okay, so before I do this, I need an interlude since the proof needs Jetspaces. So let me see what time I have. So I'm going to go maybe quick through this. So you guys know what a derivation is. I don't really need too much of this. Maybe I'll come back to it when I get there. There's a way to talk about Jetspaces as being adjunctions, right? There's a composition product thing.
There's no need to rush. We have one more hour.
I was just
we have an hour. Okay.
An
okay.
hour, yeah.
All right.
Why'd you
Okay.
go back?
Okay. So I thought since we started late,
Yeah.
no. Okay. So let me go here then. Okay. So we have so a derivation can be so a derivation on a ring A. Okay, is the same thing. Okay, sorry. First of all, I need to define this functor. Okay, so this is the dual number functor. Okay, hello, everyone, meet the dual number functor. Okay, and so it takes a ring and it makes a new ring, and you just adjoin t and mod out by t squared. Okay, and so a derivation is the same thing as a section of this natural map. So you can mod out by t here and take a section here. Okay. And so this is, and when you take a section of this is the same thing as giving a derivation on your ring A. Okay? we can generalize this. Okay, so a ring scheme, right, is a functor like this. It's like one of these. This is an example of it. And there's a natural transformation to the identity. So it has a projection like this. Okay? And so an action, right, on a ring C will simply be a section of this map. And that's all we're going to say. That's what an action is. Okay? So we can, yeah. So that's what we're going to define. Okay, and so there's a couple functors that you can choose that are kind of natural to do. Okay, so this one gives you derivations, this dual number ring. So if I look at the truncated Witt vectors of length 2, this gives Alex's p derivations, and for this reason they could be thought of as Witt differentiation. Okay, I don't really need this. I'm not going to need this right now. So I just wanted to let you guys know that this is there. Okay, so this is if you take this functor, this is the same thing as giving a ring endomorphism. And so there's these things called lambda rings. And if you take this functor, this big Witt vector functor, you get lambda rings. And so there's a whole bunch of, like, pretty much almost all operations you can think of on rings, right? Rings with extra operations can be devised in this way, even when you impose relations between them. Okay? All right. So, okay, so how do we make jet spaces out of these things? Okay, so what we can do is we can take R to be an affine ring scheme. So that means that R is actually going to be represented by, so there's two viewpoints here. One is as a functor, and one is as a scheme. Okay? And so it's functor of points, so it's like a group scheme, right? Or an algebraic group. You plug in some points and you get a group out. So if you plug in some points into this thing, you're going to get a ring out, right? And it turns out that when you have one of these guys that's representable like this, there's an adjoint, okay? So here, if you think about this again, and this were the dual numbers, you'd have a map to the dual numbers, right? And this would be like a derivation here, okay? And so here, right, there's a space whose B points are derivations, right? Or the same thing as derivations. And so this thing here is actually the tangent space in that case. And more generally, these are what I call jet spaces. So whenever you have one of these things, so in the affine case, right, you can cook up a jet space by looking at this adjoint. All right, and so this bifunctor here is called the composition product. So all you should think about is like, this is some way of, this is like all your extra operations, and they're kind of, you're composing them with this ring A, okay? So, for a scheme, okay, we can define a functor of jets, right, to be like this. So this is the Q jet space, the jet space associated to this biring, or so, okay. So when this Q is there, so I don't know if you guys remember, if you have a group scheme, it's the same thing as being a Hopf algebra, right? So group schemes are spec of a Hopf algebra, right?
Linear ones.
Projective. So for projective ones, you have some stuff on the structure sheaf. Yeah. So in the affine case, exactly.
Okay.
So in the affine case, right? Yeah. In the affine case, you're going to have something that's like a Hopf algebra. You're going to have two co-multiplications. You're going to have a co-addition and a co-multiplication, two co-units, and maybe an S, which is an involution for the addition operator, so the negative, okay, and then they have compatibility between them. Okay, so blah, 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 okay, this is a way of doing this. This is kind of boring. Okay, so you have these jet functors. I guess here's an open problem, is that you define these jet functors, and it's an open problem to determine which one of these are representable. So, so we know for Witt vectors they are, right? And we know for, say, power series things they are, right? But in general, we don't know when these things exist as schemes. Yeah. All right. So, okay, I did this. There's also a relative version of this construction that you can make. So if you're given an action, right, you can talk about prolongations of an action. And so prolongations, right? So what do you expect, right? So you have a section of so you have sections that are compatible in a natural way. Okay, so you fix some action on the base. You start with some action, and then you'll say that that this action from A to B is a prolongation if you have a map like this. Okay, so that's that. So all right, and so adjointly, there's this description here. So you can take the adjoint of this whole situation and write it down in terms of the jets. All right, so okay, so then you can also develop a notion of a relative jet functor as well. Okay, so you can define what it means for a point to be a prolongation point, and then define these functors to be like functors which consist of the points that prolong them. So this is the same way that the twisted jet spaces, those arcs have to prolong the derivation on the base. And so this is another way of writing it down. Again, we don't know when these exist as schemes. So you plug in a scheme, right? We don't know when these exist.
But they do for width vectors.
They do for width vectors over
some
Z.
base, over a scheme.
Yeah, in general. And so without p-adically completing. So Alex p-adically completes, but you don't need to, but you should, right? The action, right? So yes, you can, but it gets really ugly, right? When you don't. This is a problem with localization. Okay, so here are some versions here. You can have these truncated jet spaces, and then I call the infinite ones arc spaces, but everyone has their own terminology for these things. Okay, so that's that. All right, so that's the end of the jet space introduction. So now I'm going to talk about this proof of the geometric Mordeau-Lang. Okay, so there's 3 components of the proof, okay, that go into this thing. There's Monon maps, right? There's a descent trick. So this is the heavy-duty piece, and then there's these UNO tricks. Okay, so and so I'm going to have to explain what some of those things are. First, okay, so I need to maybe explain some notation here that I didn't introduce. Okay, so but let me say this first. Okay, so we're going to work over field of the derivation, and let's just, for simplicity, take it to be differentially closed, like really, really big. And so what we can do now is, if you take a finite rank subgroup, it turns out that for every single one of these,
Oh, when you have a chance. So you're giving an outline of the proof of the Mordeau-Lang.
Yeah.
And who's this proof due to?
This proof is due to Alex Bouillon.
Okay.
So this proof is, and so this proof, so I've kind of patched things together from a bunch of different things. So this is so this is not a new proof, but I guess its presentation is a little bit new. Okay, so what was I going to say? Oh, okay. So the whole point is that you can take the Colchin closure of finite rank subgroups, and they live inside kernels of differential algebraic maps. So morphisms of differential algebraic groups. And that's kind of crazy. That's cool. It's really amazing. What's amazing is that, so what you can do is you can take this differential algebraic variety, right? And by this I mean this is the corresponding thing in the infinite jet space, the infinite arc space. Okay, so these are these equations here, right? And it turns out that this thing's of finite type, right? So this is a finite thing that's living in this infinite jet space, which is cool, which is really cool. Okay, so I think that's, so this is kind of pretty cool. Okay.
Finite type in what sense?
I don't understand.
So it's a finite, so the dimension of this as you can take this into the infinite dimensional jet space of the abelian variety, right? And when you look at the equations here, right, it'll be finite dimensional, meaning that after,
is it algebraically finite type or differentially?
Differentially.
No. Algebraically.
You mean when you take the prolongations?
Yeah, when you take the prolongations. Yeah. So when you take the prolongations, they end up. So like when you go to the, let's say r plus, or let's say 2 times the dimension of the abelian variety,
right,
plus the rank, right? Then it starts to stabilize. So after that, it becomes an isomorphism, right? So after you go past this space, it ends up being this finite dimensional thing all the way up to the top, right? Which is cool.
In differential algebra, sort of naively,
Yeah.
that's a finite dimensional differential algebraic group
Yeah. Okay. Well, yeah. So it's cool.
without any jet space.
Yeah. Okay.
Yeah.
All right. Well, yeah. All right. Cool. All right. So so back. This was supposed to go back down. So this is one of the ingredients. All right. Okay. So the other ingredient that goes into this is these UNO tricks. Okay. So now I need to talk a little bit for a second about Kadir dimension. So maybe we can switch over here.
Oh, yes, just a moment.
Yeah.
I think the
The light.
Oh yeah.
Oh, so
the algebraic equations and the prolongation is exactly the
Exactly.
differential algebraic
Yeah, I
equations.
understand.
Yeah.
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 But I don't think in those terms. It's the same.
But it's literally the same equations.
Literally, yes. Yes, you get.
It's just the
when you
new
put all
variables
together.
are
Sure. Yeah.
the the
Exact,
formal derivatives of the
Monon's
variables.
equation. Yeah,
Yeah.
you get. But Ollie worked with differential polynomial functions on the original. Instead of prolongation. Well, he worked that too. That's true.
All right. So I might switch back soon, so maybe.
Oh yeah, it's okay. So
Okay.
What
I'll
have,
have the
have you
presentation.
looked at the situation for a divided power?
Oh yes.
So for the divided power Jetspaces, so I think Hershkovsky has some stuff on this, right? I don't know much about the characteristic P things. So
What is divided
there's
power?
actually an interesting jet space that nobody looks at. So there's a jet space. So there's these. Okay. So Alex has a theorem where you have these like 4 operators, right? And so so I saw a talk, and I know. So now I guess I realize what this so Dinesh Thakur gave a talk, and this 4th operation is actually really rich and interesting. And not much is known about it differential algebraically, and it should contain a lot of information.
Oh.
And so, maybe I can show you guys real quick. But yeah, okay. So if I take A to B, so this is just an aside real quick. Maybe this is inappropriate to do in the middle of the talk. But okay, so this is a prime ideal. Irreducible polynomial. Okay, the extra operation on this space. Okay, so like if you take A mod P, this number is equal to Q. Okay, so this is a irreducible polynomial, so this will be a field, right? And this is Q, right? And so you'd find delta P of A to be A to the Q, or A minus A to the Q divided by P, right? And this is actually an operation, right? And it's linear, so you can do all sorts of stuff with jet spaces with these, and not much is known, right? So this is, you can do width vectors with them too, I think so, which is kind of interesting. They should be like related to power series, but anyway. So back to Kadir dimension, okay? Variety. Okay, and so let's say smooth for now. Okay.
Please break the chalk into.
Yeah, you might be using the wrong.
Oh yeah. I have the fancy one. Okay. So you have this a variety here. Okay, and then there's oh man, I used K. Well, okay. So you have a canonical divisor. And then K of C. Okay. So this K of C has nothing to do with the field. This is just the canonical divisor on this variety. Okay. Or sorry, K of X.
X, yeah.
Yeah. Okay. And this, so you can so there's also a pluricanonical divisor. So this is what's called a pluricanonical. Okay, it's really just m times k of x. It's a fancy name for just taking a multiple of it. Okay, and to this pluricanonical divisor, you can take a phi of m k of x. Okay, when this is base point free. Okay, so meaning that so what you can do is you take this. And you take x, and then what it maps to is the image here, okay, of x. And this is in some large projective space. This n here is actually the dimension of this sheaf there. So like if you know the global sections where you allow poles along this, okay. So you have this thing here, and then the Canonical dimension. So when I take for large x, so it's called kappa of x. So this is equal to the dimension of the image. So let me actually here. So the definition. Okay, so the Canonical dimension is equal to the dimension of the image. So the image in general is going to be contracting for large. Okay, so once you take this big enough power here, right, it's going to give you a good, as big of an embedding as possible. And the dimension of your variety after you take this, or not embedding, but this map, right, will give you this Canonical dimension. Okay, so this is an invariant of your variety, and there's kind of some interesting things. So, okay, so that's what that is. So let me just make a comparison with curves real quick.
So this dimension is going to be at most the dimension of the variety?
Yes, exactly. Exactly. So it's going to be dimension at most, dimension of the variety. Okay? And so, so for curves, okay, so if you have positive Canonical dimension, so genus 0, so this is the same thing as Canonical dimension equal to -1. So I guess, and then genus 1 is Canonical dimension 0. And then genus 2 is Canonical dimension 1. So bigger than or equal to 2. Okay, so these are like general type. Okay, so why do we call it -1 again? So I guess so dimension 0. So I guess that you can't embed it, so that this thing will not give an embedding, and so I guess it's when it's not base point free. So so examples is like this is like P1. So yeah. All right. So there we go. So this is this is an invariant that will come up, so I'm going to fix a large M. And then look at this embedding, okay? And so this is an important invariant, okay? So the idea is there's other conjectures which say that when you're in this like large Canonical dimension case, you should have few rational points, okay? All right. Now we're gonna go back to the.
So you can start. It's showing the screen.
Okay. So so now we have some tricks. Okay. So all right. So there's kind of a tricky thing that you can do, and there's a way if you take a subvariety of an abelian variety. What you can the lights. Yeah. Okay. So when you take a subvariety of an abelian variety, there's a way to like make a kind of, so this is, you call this like maybe a canonical embedding here, or pluricanonical embedding. There's a way of getting these embeddings into other abelian varieties, right? So you can kind of take a quotient of your abelian variety and make it so that the image will be the Kodaira dimension of your variety, and so it'll be contained in another abelian variety. So this is, okay, so let me actually state these things again. So, okay, so take a subvariety of an abelian variety, right, and suppose it has positive Kodaira dimension, okay? So there's this map here, so this is this canonical embedding that I said over there. So I fixed phi, and phi is for some km, so some pluricanonical. Okay? And it turns out that the fibers of this map have Kodaira dimension 0. So there's some sub-additivity, actually, with Kodaira dimension in fibers of maps. Okay? And so it turns out, okay, that any abelian, if you have a subvariety of an abelian variety, which has Kodaira dimension 0, then it's a translate of an abelian subvariety. And that's kind of crucial. Okay? And so what you can do then is you can take up this map here, right? And you can look at the fibers of it. And so the fibers of this map, right, it's going to be a subvariety of an abelian variety, and they're going to have Kodaira dimension 0. Okay? So in particular, it says that every fiber, right, is going to be an abelian variety. Okay? And if you work in the, okay, if you work like et al. Locally, or you work in some analytic topology, right, like Alex does in his proofs, you find that this this thing here is actually a fibration. So each fiber is the same abelian variety. Okay? And there's kind of a canonical F, right? And what happens is that you can take, this subvariety here, and you can cook up a new map, right? That uses that fiber, that special fiber that's associated to your X, and take a quotient. Okay, and I'm going to call this map capital psi, because it's kind of like capital phi. And I don't mean it to look like a Monon map. Okay, so I kind of use size for Monon map, but it has nothing to do with each other. But it turns out that this map here has the same Kodaira dimension. So you have this embedding like this. Okay, so you have, I mean, not embedding, but I always say that, but you have this here. So it's kind of interesting. Okay, so you have this kind of way to cook up this special map, and then we're going to use this later. Okay, and there's a lemma of Alex's where he takes this idea of UNO, and it says that if you have an abelian variety of trace 0, then the Albanese of this new guy, this image, does not descend to the constants. Okay, so this is a trick that he uses, and he's going to use this to cook up a contradiction. And so this is what a lot of the work is. I mean, not a lot of work, some of the work. The most of the work is for this descent theorem that I'm going to show you. Okay, so this is a trick. By the way, the Albanese of a variety is kind of the initial thing that maps to abelian varieties. So out of all the maps to other abelian varieties, they always they always factor through the Albanese. So it's this guy. Okay? So it's like, yeah. So that's that. And we're going to use that. Okay. So again, there's these things. And now the big one is, so again, this is supposed to like fly over. But there's a trick that Alex uses to get descent. Okay? And the trick is the following. So you take a finite rank subgroup, you take its Monon kernel, you just take a Monon kernel, so it's something associated to a finite rank subgroup, so that construction that we had previously. And if this sigma dominates X, okay, then this thing will descend, okay? Okay, so that means that it'll descend to the constants. So remember, now I have two things. I have a condition for it not descending, and I have a condition for it descending.
What do you mean by dominates?
So dominates means this. So dominates means that if I take this map, it's just a dominant map. Okay? And you can actually take this at finite level. Okay, so a finite order because of
the finite.
Yeah, because of the finite tightness.
Yeah.
And who are those things?
So these things, so this is the Monon kernel, and so this is really the differential equations, right, of this guy. Okay? Yeah, and so this is completely algebraic, and this is the jet space of this guy. And they both live inside the jet space, the infinite jet space of the abelian variety.
Yeah.
Okay? And so this is what I mean. So this gives you a condition, so like it says if you have, like for example, this could be a lot of torsion points, right? And it gives you a condition for descent. All right, so now I'm going to put all these three tricks together. Okay, so maybe I can go to the board again. Yeah. Okay, so I'm going to show you the proof now of the
Turn the lights a little bit.
yeah. Okay. So here's the proof of the geometric Mordell line. Okay, so what we're going to do is you take, okay, so we started with a set S, okay? So S, so this is contained in a finite group, so such that this thing here is finite rank. Okay? And, okay, so what I'm going to do now is take X, a subset of, so this is the Colchin closure, okay? And then I'm going to take the Zariski closure, so this is going to be an irreducible component.
Zariski irreducible?
Yes, Zariski irreducible. Okay? And
How
it's
are you doing that? Taking the Colchin closure? Are you moving into
just
the,
points. These are
into
just,
the jet?
no. So
What do you mean by Colchin
So
topology?
so what I mean is I take it on. So this is so S col
He's always working over it.
is a subset of AK, right?
But
And
it's, you have to put the Colchin topology on. but-
yeah, exactly. You put the Colchin topology using the field here. Yeah.
Right.
Okay.
Aha. So there we're returning to
Yeah,
different
yeah,
geometric
yeah.
groups.
Yeah.
Good.
Yeah. Okay. Yeah.
Yeah.
Okay. And so so you can do that there. I think there's another way of doing it. I think in the arc
Can you-
spaces too.
Yeah. Can you?
Yeah.
Yeah.
So.
Mutatis should be the same.
So Colchin. Yeah. So I guess you just take the equation. So I guess it would be the Zariski closure of the.
Of the prolongation to a certain point.
Yeah.
Right.
Yeah.
Maybe.
I think so. I don't know. Let's just do this for now. Let's do this for now.
No.
Okay. And so so it suffices to show.
Yeah, I think so. Everything's smooth. Yeah.
Show that X is a translate of an abelian subvariety. Okay, because every irreducible component in a configuration looks like one of those translates. All right. Okay, so suppose not. So am I on over here? Yeah. So like. B plus A. Okay, so suppose it doesn't take this shape. Okay, then we're gonna derive a contradiction. Okay, so like I said, everything that has Cartesian dimension 0, which is a subvariety of an abelian variety, is an abelian variety itself. Okay, so we know in particular that this has positive Cartesian dimension. Okay, so this condition here, okay, implies that the Cartesian dimension of X is positive. Okay, and so this thing here is really the dimension of phi of X, which is also the dimension of this psi of x. Okay? And so psi of x, again, was this thing where we quotiented by the this canonical fiber.
Yeah.
Okay? And so, so by Boolean's lemma, so there's this lemma that he said, so again, we're assuming that A is nice, so we assume that it was non-isotrivial, right? So there's this lemma of Boolean that says that the Albanese, the psi of x, does not descend. Okay, so it's not, yeah, so it does not descend. All right, and so so this implies that x does not descend because the field of definition of the Albanese is the same as the field of definition of your variety. So this implies does not descend. Okay? So in particular, this implies, so by Boolean's other, sorry for about your shock. So by the descent lemma, or so by the descent theorem, so this is the trick where if you're dominated by a Monon kernel, right, then you descend. Okay? But this thing doesn't descend, so it's not dominated. Monon kernel. Okay? So in particular, so this implies that x does, so actually, let me do this the other way, sorry. So this doesn't descend, so, sorry, I should say this now. I skipped this down. So x doesn't descend. If it did, right, then this would descend, and you can't have that. So this means that x is not dominated. Okay, so this is the Monon kernel. Okay, and so in particular, x, right, we took it to be, okay, so when we started, we took an irreducible component, right, and then of this thing, so this is contained in the Colchin closure, or this contains the Colchin closure, right, so we have this equality here, okay, so we started out with an irreducible component of the Zariski closure, okay, and so, so this thing here is contained in the image of this, all right? And we know that this thing here, so this is the natural map from the infinite jet space down to the bottom. We know that this is not dominant, so this is a subset not equal to x, okay? So then this is a contradiction, right? And that finishes the proof, okay? So, so that's the idea there.
Why is it true that if it's dominated by Monon kernel, then it descends? Why?
Okay, so that's, yeah. So I have notes on that. So yeah, so this is, it follows essentially from a version of the Picard theorem, and so there's this other there's a theorem of Ham, which allows you to, it kind of is a similar trick where you have like a fibration, and then you have that it has constant fibers. So it's another rigidity trick, right? And so, in particular, what's interesting is that in the arithmetic case, there are replacements for the Picard theorem, right? But the Ham's theorem seems to be a sticking point, right? And then the Monon kernels also seem to be a sticking point. Okay, so those are some of the obstructions to effective Mordell. Yeah. All right. So maybe we can go back now. Okay, so yeah, so there's those three tricks, right? And they come together to give you this. The hardest one is the descent, and this is what uses the Picard theorem and everything. Sorry. All right.
You can
All
consider
right, all right.
this.
So, okay, so now the question is, how do we make this effective? Okay, so we have this proof, and how do we get it to be effective? All right, so, goddamn. Okay. Again, the algebraic closure